Hello, this is the presentation of D2V Perception and Control System designed for autonomous parking. Our team will proceed with the presentation in the following order. This system is for various parking situations such as 90-degree parking, parallel parking, and diagonal parking. To detect these various parking situations, the autonomous parking system detects parking spots using camera depth estimation. First, safety issues due to numerous blind spots and poor parking skills can lead to accidents. Second, incorrect parking contributes to parking space shortage and social conflicts. These problems can be solved with our system. This is an overview of the project. The goal of diagonal parking is to park in the red target range shown on the left. The picture on the right is a picture of our car diagonally parked in the Mirai simulator with the code we set. The goal of parallel parking is also seen in the left. In order to verify the diagonal parking code we have set, we modified the code a little bit. Due to location constraints, we set our real goal to park in Songdo's perpendicular parking space. The above figure is a ROS RQT graph. The EKF GPS IMU uses a positioning sensor to locate my position. Hannah Corner extracts the vertex with the camera, the basis for path generation. Using the above information, we apply the algorithm and send the control information to the ERP through serial I/O. Our team is largely divided into planning and control, vision, and positioning team. These are the main algorithms of the planning and control team. First, diagonal parking. The car recognizes corner points and starts generating path. It obtains a point that meets the entire path based on the focus of the two corner points. After reversing to an appropriate distance, the route is generated by applying the cubic spline algorithm using the previous calculated point, current position, and parking endpoint. Next is the parallel parking path. First, the car recognizes corner points and starts generating path, then sets the starting point at the last corner with an appropriate distance margin to create a path that takes into account the minimum radius of rotation, so that it can be parked in the middle of the parking compartment. To recognize and send the relative coordinates of the actual corner location, we used image undistortion and saved rotation metrics and translate vector to convert pixel to world coordinates. Next, we built a dataset for corner recognition. Finally, we converted the coordinates of the bounding box into world coordinates in real time and communicated ROS with the planning team. Here is the world coordinate system for your understanding. A corner point is obtained by creating an imaginary XY axis with the camera position as the origin. It is the midpoint of these 2 points that is sent to the planning team. The localization team is responsible for determining the position and heading of our vehicle. Our team achieves this by using a GNSS sensor with a positioning error of less than 1.4 centimeters. Localization also employs sensor fusion with an AHRS sensor and GNSS sensor using an extended Kalman filter to obtain more accurate heading values. The vehicle's speed is determined using rotary encoders, and in areas with weak GPS signals, dead reckoning is utilized to estimate the vehicle's position. Localization teams send the vehicle's position, heading, speed, and other information to the planning and control team using local messages. Here is a video showcasing our team system. To see the full video, please refer to the URL below. Professor Kim Ha-gil served as the supervising professor, and senior researcher Park Jae-hyung act as the mentor. Each team is structured as follows. In the early stages, our team focused on hardware implementation and technological development. Subsequently, we integrated the technologies from each team and conducted field tests to establish the overall system. These are the problems we are going through and the solutions. For planning and control, first there was error due to sudden stop. Using predictive control, we will plan the speed to stop slowly. Secondly, the parameter values of per pursuit algorithm are different when reversing and advancing. Therefore, we are working on applying a Stanley algorithm. Lastly, we need a way to modify the path when it doesn't go the right way. Another camera will be installed near the rear axis to keep feedback on the distance to the lane. The vision team's biggest problem was coordinate errors. Through cause analysis, we could see the problem was the rotation matrix obtained during the calibration process. Therefore, the error was reduced by taking feature points around the expected parking corners location to obtain the optimal matrix. The blue line on the graph represents the heading obtained through the extended common filter. As can be seen from the graph, it indicates the deviation that occurred. In the localization team, we addressed the fluctuation in the heading obtained through the extended common filter by applying a moving average filter. Through depth estimation and cubic spline, this system is accurate. By applying this system in autonomous vehicle, we can expect more convenient and safe parking. Thank you for listening.